Hello, my name is John Fortner, and this is my video report for Lab 3 Magnetic Field of a Bar Magnet. Lab 3 Magnetic Field of a Bar Magnet investigates the shape and magnitude of the magnetic field of a bar magnet as a result of its magnetic dipole moment and the distance and direction away of an observation point from the magnet. This lab relies on formulas for magnetic field of a magnetic dipole, both the general formula as well as, for a simplified case, for an on-axis observation point. And we use these formulas to derive a value for our magnetic dipole moment and to create a computational model that calculates the magnetic field at a variety of observation points. This lab will observe the magnetic field produced by the dipole at several points on axis, as well as at one specific point at a 45-degree angle off axis. We suppose that the magnetic field depends on the product of some constant and an exponential degree of the distance from the dipole, denoted b equals k r to the n, where k is the constant value, r is the distance from the dipole, and n is some constant that represents the exponential degree to which b depends on r. And then we use the natural logarithms to find both the degree n and the value of the constant k, found by the equation natural log of b equals natural log of k plus n times the natural log of r. Here's the data for our experiment. Here we wanted to find the distance at which the magnetic field produced by the dipole was a certain value, and then we found the distance at which that value was produced. So here we graphed those values. We graphed the ln of r, the distance, with the natural log of the x component of the magnetic field at each point, and we found this equation y equals negative 2.8587x minus 14.177. So this negative 14.177 is our constant k, and the negative 2.8587 is the constant n. And then here we also observed the magnetic field at the point 45 degrees off axis, which we found to be 2.1389 times 10 to the negative 5 Teslas. So from our observations, we can obtain a value for k, which allows us to solve for the magnitude of our magnetic dipole moment. We suppose that our constant k is equal to the constant for magnetic fields, which is mu naught over 4 pi, times the 2 times the magnetic dipole moment, which we denote mu. And from there we solve for mu. And we obtain for mu 3.4832 amperes meter squared. We can then plug our value for mu into our computational model, and this model uses the general formula for the magnetic field produced by a magnetic dipole, which is presented on the screen. So here's our code for our computational model. Here is where we plugged in our magnitude of mu, and then here is our function that calculates the magnetic field produced by the dipole some distance r away from the dipole. And then all these lines create these arrows that represent the magnetic field at a variety of different points in the model. So here we'll go ahead and run the program. And here we see these arrows representing the magnetic field at those points. So the orange arrows represent points that are on the axis of the dipole. The blue arrows represent locations that are perpendicular to the dipole. And then this purple arrow represents the distance that is 45 degrees off the axis of the dipole. And this purple arrow is what we compare in our console with the magnitude of the field that we observed in the experiment. So we found that our model that calculated a value that was 2.2 times the experimental result. So our model calculated the field to be 2.2 times greater in magnitude than the experimental result, which means that our model was at least in the correct degree of magnitude, although a bit off. And we can expect a certain amount of error because we had a discrepancy in our value for n in the experiment, because from our experiment we observed that our value for n was about negative 2.85, whereas in the computational model we used the number negative 3. So it would have been surprising if our values had been too similar, but the fact that our model was in the correct degree of magnitude is very reassuring. And finally we have some additional questions. So one, what if you hadn't oriented your experiment to compensate for magnetic north and then instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? Well, assuming we could accurately calculate the appropriate impact of Earth's field and correct accordingly, then the results wouldn't actually change. It just would have been a lot more difficult to correct compared with what we actually did in the experiment. But without additional correction, the magnetic field of the Earth would have contributed to the net electric field from our observation, which would have distorted our results by overestimating the field produced by the dipole. And then what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? Well, the two magnets would produce about double the field of just the single magnet. And that's all. Thank you very much for watching.